So welcome to lecture number 18. So in this particular lecture, we are going to start with the uncertainty principle. All right, the uncertainty principle. So what is basically an uncertainty principle? So for example, if you want to, normally we want to measure something, we use light, for example. Say we want to measure the position of electron. So what you do is that you shine a photon on this electron, right? So using light to measure. Correct. Okay. So now, any process of measurement, measurement, okay, leads to an inherent, uncertainty in position of electron. Got it. So if you look at now the expression that P is equal to H by lambda, P being the momentum. So if you make lambda smaller, that means you progressively use light of smaller and smaller wavelength. Okay? This leads to a greater momentum of photons. Okay, so if you make lambda smaller and smaller, say you are making it smaller and smaller, lambda being smaller and smaller, greater is the momentum of the photons. And this means that this will cause the electron to displace even further. So you understand the dichotomy here. You are using light to measure, say, the position of the electron. So what you want to do, you want to make the light smaller and smaller and smaller so that you can measure the position of the electron more precisely. Right? So the wavelength of the light is being made smaller and smaller. So you want to go like this, right? And then you want to decrease the wavelength even further, right? So, but any process, what will happen is that the photon is getting bombarded on the electron. So the electron's position is going to be moved because of the impingement by the photons, correct? So you want to avoid that. So what you want to do is that basically you want precision, which means you have to make lambda smaller. But the moment you make lambda smaller, the momentum of the photon increases. And so that means it is hitting the electron. If the electron is here, the photon is hitting the electron with a higher momentum. That means it will cause more displacement. So as a result of that, just by making the the photon wavelength smaller and smaller is not going to serve the purpose in this particular case. All right. So this sets the stage for Heisenberg's uncertainty principle. So the next page, Heisenberg's uncertainty principle. Again, a cornerstone of quantum mechanics. So Heisenberg's uncertainty principle. So what Heisenberg's uncertainty principle states is that it is basically a limit on the precision, with which two dynamic variables can be measured So two dynamic variables can be measured whose quantum mechanical operators Those quantum mechanical operators do not commute. Those quantum mechanical operators do not commute. All right. So let us take two dynamic variables. Two dynamic variables. Variables A and B. Okay. So A hat, B hat minus B hat, A hat. So these are two dynamic variables A and B, and these are their operators given as, say, C hat. They do not commute. They are quantum mechanical operators, which is A hat and B hat. They do not commute. So there is a limit on the precision with which two dynamic variables can be measured where the quantum mechanical operators do not commute. Okay? So the two dynamic variables are A and B. A hat, B hat are their corresponding quantum mechanical operators. So if they do not commute, this is what we can write. Now, delta A equal to, okay, this is some kind of an RMS deviation. So you saw what this is. It is the dynamic variable minus the average of that particular dynamic variable, square of that, and then you take the average, and then you take the square root of that. This is RMS deviation. So therefore, now delta A into delta B, delta A into delta B is basically the deviations, the RMS deviations of those two quantities that you are trying to measure. So maybe we should go to the next page because it's a longish expression. Delta A into delta B is equal to star A hat bar square star. All right. That is what it is, because it is acting. This is the operator that is acting on the wave function. Okay. So, and similarly, the other expression is phi star B hat delta square down raised to the power of half. Okay, so A hat and A are Hermitians. Hermitian operators. A and B respectively. Okay. So you can see that this is what it is. Okay. Now, if the operators are Hermitian, we can do a cool thing here. So say this is an arbitrary. So this is a rule. So if tau equal to, get this, G if tau. This is for the Hermitian operators. This should be valid. Okay. Now let us assume in this case, D hat is A hat minus A bar. And G, let's assume, is the wave function. Okay, and F is nothing but A hat A plus star with acting on the wave function. Okay, so therefore, once we get these rules all set, okay, so delta A into delta B given as A hat Then of course you have raised to the power. That thing is raised to the power. Okay, so you got this expression. This comes by applying the Hermitian operator rule, right? So we have just used this rule to go from here to here. Okay, so that's really nice. Now, Schwartz. W, Schwartz inequality states for any two well-behaved functions, okay, this should be valid. F1 or F1 beta into F2 or F2 beta should be greater than or equal to the mod F1 star into F2 down squared. Okay, so this should be the validity of the Schwartz inequality. So Schwartz inequality is important. So we saw that we use the general Hermitian operator rule to take this kind of a quantity, which is basically nothing but the product of the differential or standard RMS deviation in dynamic variable A and B, and we have substituted it and we have cast it therefore in this particular form. Okay, in this particular form like this. Now Schwartz inequality states that for any two well-behaved functions, this is what we are going to get. Okay. Got it? Okay. So this is Schwartz inequality. So therefore, delta A into delta B must be greater than or equal to mod so this is as a bracket, then this becomes star, okay, into B hat. This does not require the star. It's the theta. Okay, so all we can say is delta Z equal to delta Z. This is also true. So what we can say over here is basically we have used this Schwartz inequality to get to this particular form. And this is just a definition of Z, modulus of Z, which is basically the quantity within bracket. We will show it in a little bit what it is. So delta A into delta B must be therefore greater than or equal to 2i. Put a bracket here. To B beta minus 2 over 2i integral B star right over and then put a modulus here. Okay. So now go to this is what has been planned here. Okay. Now, so if we move it further now, therefore, delta A into delta B must be greater than equal to 1 A bar into B minus total leverage I theta. Okay. Now, further, delta A into delta B, therefore, this part is equal to theta. Okay. Therefore, delta A to delta B is greater than equal to. So it is greater than equal to C bar by 2. That is what you get. So that is what the inequality between two dynamic variables whose quantum mechanical operators do not commute. It is. Now let's take the example. Let's take an example where delta A is basically delta X, delta Px is delta B. So therefore, this is the momentum, and this is the position. The error in position, the uncertainty in position, and the uncertainty in this is given in this particular fashion. Okay. So now, so in this particular case, and this is left as an exercise, one can show that delta X into delta Px is greater than equal to h bar by 2, which is given, this is the Planck's constant. So that means if you want to reduce the error in, say, delta X, if you want to measure the position more accurately, that means this becomes smaller. Okay, then this has to become larger for this to be valid. It has to be greater than the Planck's constant. So, but this is left as an exercise. You should find out what are the operators. Basically, you have to find out X hat and Px hat operators. And we already know what those operators are, can be those operators. Using these operators, you're supposed to find out that what will happen to delta X to delta Px. But the overall answer that is given is delta H by 2. Delta H by 2 is the answer. Okay. So what we have seen over here in this particular exercise is that we have used non-commutative quantum mechanical operators, and we have shown that this is the most generalized expression between two quantities, dynamic variables, and these are basically the RMS deviations of those quantities. They must be greater than equal to some value. So this is not 0, this is some value. Similarly, like this is not 0, this is some value. Okay, so you cannot measure something with what we call a great deal of certainty, because the precise position cannot be measured. If you want to measure the precise position, then the position in the error or the uncertainty in your momentum, for example, will be huge. Okay, just to keep track of this inequality. Okay, so this is an important piece of information that we have right now here. Okay, now let us take a look at two other things. One is indistinguishability and symmetry. Okay. So fundamental particles can be counted, but they are inherently indistinguishable. Okay. So for example, psi equal to psi R1 which are independent independent particles. So psi is like this. Okay, so if we exchange two position vectors, so that means you interchange. So psi becomes equal to R2, R1, up to Rn. Okay. Physical observations remains unchanged. Okay. Physical observations remain unchanged by any virtual math operation. Okay. So the physical observations are dependent on star shine and cannot be affected by particle combinations. If the particles are truly indistinguishable. The particles are truly indistinguishable. Okay, this can be guaranteed. You understand this? So the particles, as we say, that even if we exchange their positions, okay, because they are indistinguishable, so there is no change in physical observations and nothing changes. So everything remains the same. And since it is dependent on this is not affected. So this can be guaranteed if psi R1 continued to n is plus is sorry. It's equal to plus minus psi R1. So the wave function must be symmetric or anti-symmetric. So the wave function must be symmetric or anti-symmetric with respect to exchange of two particles. Okay. So for n particle system, okay, there are n factorial permutations that are possible, right? So if we define PR hat, the permutation operator. Permuting one order of position vectors. So permuting one order of the position vectors. R1, R2, Rn2, R2, R1, okay. For n particle system, number of such operators n factorial, number of such operators n factorial. Okay. So delta PR, the number of two particle exchanges required to bring the order, okay, specified by PR hat. Specified by so two successive exchanges of two particles having anti-symmetric wave function okay, will yield the original wave function. So say P1, say it's like say any combination 1, 2, 3. Okay, P2 is 2, 1, 3. Okay. Then of course there is P3, which is 3, 1, 2. And P4 is 1, 3, 2. P5 is 2, 3, 1. I'm just giving an example, a random example over here. P6 is 3, 2, 1. Okay. So delta P1 is obviously equal to 0. Delta P2 is equal to delta P4. Delta P6 is all equal to 1. And P3 is equal to P5 is equal to 2. Equal to 2. So, in other words, PR, when it's acting on a wave function, should give you plus minus delta PR. The electrons and protons have anti-symmetric wave function. Whereas bosons have symmetric wave function. Okay, so this is the general rule. So you can see that what it will yield, right, when you actually have indistinguishability and we have this is obeyed must be either symmetric or anti-symmetric with respect to exchange of two particles. So we finish our lecture on uncertainty principle and symmetric and anti-symmetric wave function. Next class we are going to do Pauli's exclusion principle and few other things in details.